Today we're going to learn how to use a binary tree. Hello, I'm James Helfrich. Using a vector or a list, a set or a map, it can be really easy because the authors of these containers have carefully created interfaces to hide the messy implementation details. Using a linked list or a binary tree, on the other hand, is not so easy because we have to manage those details ourselves. We have to make sure that we set the pointers correctly. Today's video is going to demonstrate how to do this with a binary tree. There are three constructors provided with the B node: the default constructor and the copy and move constructor. The copy and move constructor take a t as a parameter. In order to use the binary tree, we first have to pound include our B node library. Now this is not built into the standard template library. We got to create it ourselves. That's why we use the double quotes rather than chevrons when we pound include it. Now my class name is bnode, is a template. This will be a type int. And when I say b, this will call the default constructor, which I expect the value to be 0 because that's the default value for integer. But now I can also call the copy constructor. In this case, I'm going to set the value to 50. Now I expect the value to be 50 and the p parent, p left, and p right to all be the null pointer. We don't usually create a B node, we create a pointer to a B node because binary trees are usually made of pointers. So now I'm going to allocate a B node, and once again I'm going to use the non-default constructor, setting the value to 50. So now I have a pointer to a B node. Notice how p left, p right, and p parent are all set to null. If I want more than one element in my binary tree, I have to add them myself by manipulating the pointers. Now I'm going to add a pointer to a node to the left of my root, and I'm going to give it the value 40, and I'm going to add one to the right also, and I'm going to give it the value, right, and I'm going to give it the value 60. Now when I run this, we're going to notice that p is going to have the value 50, left is going to have a pointer, and right's going to have a pointer. Problem though, the p parent is not set, and I have to manually set this myself. So I'm going to say p left arrow p parent is going to be myself, which is p, and also p right arrow p parent is going to be myself, which is p. Now when I've set these pointers up properly, now each node is going to have a pointer to its left and right node as appropriate, but also its parent node. And it's really important that we set these pointers correctly, otherwise we're either going to orphan a node, which means we can't reach it anymore, or we're going to have a pointer to something that's not valid. There are two functions associated with assigning values to a binary tree. There is assign, which will copy the values from source in the destination, reusing as many of the destination nodes as possible. And there's copy, and copy generates a brand new tree. To demonstrate how this works, I'm going to rename my P tree to P source. I love the rename feature in Visual Studio. Okay, and now I need a destination as well. So I'm going to call this guy pdest. And what's the data type? It's a bnode pointer. Now I'm going to say pdest equals copy psource, and this will generate a brand new tree from the source's values. The important thing to note is I'm going to generate brand new nodes. I'm not just copying the pointer over, but psource and pdestination have different addresses, but they have the same values. So I went from having 3 nodes to 6 nodes. Okay, now what happens if I give pdestination its own node? In this case, I'm going to allocate a new node, and I'm going to give it the value of 99. Okay. So now I'm going to say assign, and I'm going to assign the source data into the destination data. Now what assign is going to do is it's going to reuse the node that pdestination already has and just put the value from the head of source in there, and in addition to that it will generate new nodes as well. And assign will also work even if destination is a null pointer. In this case, assign will work just like copy. Since destination had no nodes to begin with, it's going to generate all new nodes. There is no iterator provided with a binary node. We have to write the code to do this ourselves by traversing the tree using pointers. There are no access functions provided with a binary node. You can access the values of the binary nodes directly because the attributes are public, and the attribute is called data. There are 6 functions provided to help you add nodes to a binary tree. There's the add left where it copies a value. There's add left where it moves a value. The same thing with add right, copy and move. And there's also the add left, which adds a subtree, which takes a pointer to a node as a parameter, and the same thing with add right. To demonstrate this, we'll start with a single node with a value 50. And we're going to call add left, taking p, the root node as a parameter, and then we're going to add the value 40. And then we're going to say add right, p once again, and we'll add the value 60. Now when I run this, then we're going to see that, that p has a left and has a right, and notice how p parent is properly set. And so all the pointers are hooked up correctly, which is exactly what we want. I can also add a node to a binary tree, not by adding a value, but by adding a pointer to an existing node. So to do this, I'm going to allocate 2 nodes, p left and p right, and I'm going to give them some value, let's say 30 and 70, okay? Now I'm going to add left, not the value 40, but p left, and add right, not the value 60, but p right. And what this is going to do is I'm going to take the nodes that exist, notice p left and p right already have a value, and I'm going to hook them up. And in doing so, then p parent is also set the way we expect it to. There is one method to clear or remove nodes from a binary tree. It's called clear. And this will delete the current node and everything below it in the binary tree. To demonstrate this, I will create a binary tree with 7 nodes. I've added that left and added right to create it. And notice I created a comment to reflect the structure of this tree. Now if I say clear p, then I expect all these nodes to be deleted. So initially, I'm going to have my binary tree with a left and a p left and a p left from that and so on. I'm going to have lots of different values. And the whole thing is filled in just like we expect with p parent set appropriately. Now, when I say clear, then notice how p is now the null pointer. In other words, everything got deleted, which is exactly what we expect. The last function provided to help us manipulate a binary tree is size. And size will compute how many nodes there are from the current node on down. So I'll start with the same 7-node binary tree I had before, and the return type of size is size t, which is an unsigned int. And when I call size on the root node, I expect to have the value 7. And sure enough, when I run it, I have the value 7 because there are 7 nodes. But I don't have to call size on the root node. I can call it on anywhere I want. In this case, I'm going to call it on p left. Now notice there's going to be 3 nodes under p left, which is going to be 4, 2, and 6. And sure enough, s equals 3. I can also call it on p left arrow p right, and this is going to be on the node number 6. And there's only 1 node there, sure enough. And I can even call it on the null pointer because node 6 has no p left, and that will give me size 0. You can learn more about the binary tree, including the implementation details of the many binary tree functions as well as applications of the binary tree in the C++ Data Structures textbook.